Hello everyone, welcome to Cryptology Kit. In this presentation, I am going to discuss greatest common divisor or the GCD of any two integers and the Euclidean algorithm. Let's start from the definition of greatest common divisor. The largest positive integer that divides both a and b is called greatest common divisor or the GCD of a and b. The GCD of a and b is denoted by a, b in closed parentheses, or GCD into parentheses enclose a, b. In this course, throughout we will use the notation a, b enclose parentheses for the GCD of a and b. For better understanding, let me do some examples. The example is what is the GCD of 48 and 72. The positive integer which divides both 48 and 72 are 1, 2, 3, 4, 6, 8, 12, 16 and 24. You can verify that these integers are the common divisor of 72 and 48. In the list of common divisor of 48 and 72, 24 is the largest integer. Therefore, the GCD of 48 and 72 is equal to 24. In the second example, we have to compute the GCD of 19 and 72. Since there are only two positive divisors of 19, that are 1 and 19, and 19 does not divide 72. Therefore, the GCD of 19 and 72 is equal to 1. The question is how to compute the GCD of given any two integers. Let a and b be two integers. If a is equal to b is equal to 0, then the GCD of a and b does not exist, because both the number are 0. If a is equal to 0 and b is not equal to 0, then the GCD of a and b is equal to absolute of b, because 0 is equal to absolute of b times 0. So absolute of b divides 0. There are two possibilities, b can be positive or negative. Here we will discuss both the possibilities. If b less than 0 implies if b is negative, then b is equal to absolute of b times minus 1. So absolute of b divides b. If b greater than 0 implies if b is positive, then absolute of b is equal to b times 1 implies absolute of b divides b. In both cases, absolute of b divides b and absolute of b divides 0. So the GCD of a and b is equal to absolute of b if a is equal to 0. If b is equal to 0 and a is not equal to 0, then the GCD of a and b is equal to absolute of a. If b not equal to 0 and a not equal to 0 with absolute of a less than absolute of b, then to compute the GCD of a and b, first list all positive divisor of a. The largest integer of these that also divides b is the GCD of a and b. For example, if a is equal to 10 and b is equal to 65, here the absolute of 10 less than absolute of 65. So list all positive divisors of 10. The list consists of 1, 2, 5 and 10. Here 10 is the largest positive integer in the list that divides 10, but 10 does not divide 65. The next largest positive integer is 5 in the list that divides 10. 5 also divides 65. Here 5 is the largest positive integer in the list that divides both 10 and 65. Therefore, the GCD of 10 and 65 is equal to 5. Note that this method is not an efficient method for computing the GCD of large integers. The efficient method for computing the GCD of large integers is Euclidean algorithm. Now I am going to discuss the Euclidean algorithm. Let a and b be two integers. Put r0 equal to maximum of absolute of a and absolute of b, and r1 equal to minimum of absolute of a and absolute of b. Compute the GCD using the following steps. First, compute r2 by putting the values of r0 and r1 in equation star. That is, r2 equal to r0 minus floor of r0 over r1 into r1. If r2 equal to 0, then the GCD of a and b is equal to r1. Else, compute r3 by putting the value of r1 and r2 in equation double star. If R3 equal to 0, then the GCD of A and B equal to R2. Otherwise, compute R4. The general form of this algorithm is Ri is equal to Ri minus 2 minus floor of Ri minus 2 over Ri minus 1 into Ri minus 1. If Ri is equal to 0, then the GCD of A and B is equal to Ri minus 1. Else, compute Ri plus 1. From the steps, it can be seen that in each step the value of R is reducing. So for any non-zero integer, there must be a natural number k such that Rk equal to 0 and the algorithm halt for any input integers. And this is an efficient way to compute the GCD of any non-zero integers. Let me construct some examples for more clarity and understanding. For A equal to 287 and B equal to 91, since the absolute of 287 is greater than the absolute of 91, therefore R0 equal to 287 and R1 equal to 91. Put the value of R0 and R1 in equation star. That is R2 equal to 287 minus floor of 287 over 91 into 91. 287 over 91 is equal to 3.15. Therefore R2 is equal to 287 minus floor of 3.5 into 91. The floor of 3.5 is equal to 3, therefore R2 is equal to 287 minus 3 times 91. 3 times 91 is equal to 273, therefore R2 is equal to 287 minus 273. So R2 is equal to 14. Since R2 not equal to 0, therefore we have to compute R3. To compute R3, put the value of R1 and R2 in equation double star. We get the equation that is R3 equal to 91 minus floor of 91 over 14 into 14. 91 over 14 is equal to 6.5. Therefore, R3 equal to 91 minus floor of 6.5 over 14. The floor of 6.5 is equal to 6. So, R3 is equal to 91 minus 6 times 14. 6 times 14 is equal to 84. So, R3 is equal to 91 minus 84. 91 minus 84 is equal to 7, therefore R3 is equal to 7. Since R3 is not equal to 0, therefore we have to compute R4. By putting the value of R2 and R3 in the general form of the algorithm, we get the equation that is R4 is equal to 14 minus floor of 14 over 7 into 7. 14 over 7 is equal to 2, so R4 is equal to 14 minus floor of 2 into 7. Here the floor of 2 is equal to 2, so R4 is equal to 14 minus 14, so R4 is equal to 0. Since R4 is equal to 0, therefore the GCD of 287 and 91 is equal to R3, where R3 is equal to 7. So the GCD of 287 and 91 is equal to 7.